In this screencast, we're going to look at a generating rod that we looked at before. In other words, we have a rod here that is 1 meter long. The rod itself has a diameter of 50 millimeters with volumetric generation, and that's covered with a sleeve. And again, let's draw it looking this way. So what we have here is, not to scale, here we have our generation within that rod. And so we'll call this 1 and this 2. And so our D1 and our D2, it's a sleeve that's 10 millimeters thick, so it's equal to 70 millimeters. And the sleeve has a thermal conductivity of 3 watts per meter K. We have air that's blowing by it, and it's at a temperature of 25 degrees C, and it has a heat transfer coefficient that's equal to 25 watts per meter squared Kelvin. And what we're going to do here is we're going to give this volumetric generation rate, which is 1.4 times 10 to the 5th watts per meter cubed. And what we want to find is T1, which is the temperature at the interface between the sleeve and the rod, as well as T2, which is the temperature at the surface of the sleeve. The method we're going to use is the thermal circuit approach. And so what this assumes is that our heat rate, Q, has to be constant in that it is not a function of R. Our governing equation is going to be that Q equals a change in temperature divided by the sum of the resistances between those temperatures. And so where we're going to look at is from T1 to T infinity. So T1 is the temperature that we're looking for. If we take a look at the resistances that are between them, we have our T1, and then outside here we have a T2, and then finally we have our T infinity. So the resistances that we'll look at consist of that conductive resistance between T1 and T2, as well as the convective resistance between T2 and T infinity. So the first thing we're going to have to do is solve for that Q, or heat rate. And the way that we do that is that our Q is equal to the volumetric generation rate times the volume. And so our heat transfer rate ends up being 275 watts. Now we need to solve for our different resistances. So the conductive resistance is defined as the natural log of, usually it's the ratio of the radii, but here we can also do the ratio of the diameters. And this is divided by 2 pi times the K of our sleeve times our length. And this ends up being 0.018 Kelvin per watts. We do the same thing with our convective one. So our convective resistance is just equal to 1 divided by our convective heat transfer coefficient times pi times our diameter times our length. And that's going to end up equaling 0.182 Kelvin per watt. So now when we add that together, we have a total resistance of 0.2. And we can stick that in our equation to finally find that outside surface temperature. So our Q, which is equal to 275 watts, equals T1 minus 25 degrees C divided by that total resistance, and therefore our temperature is going to be equal to 80 degrees C. That's going to be our T1. Now we need to figure out the outside temperature, or T2. And here, when we're looking at it, our resistance is between T1 and T2. And if you take a look at our picture, the mode of heat transfer between T1 and T2 is conduction. So that's going to end up being our conductive heat transfer resistance. So Q is going to be equal to T1 minus T2 divided by that conductive resistance, which is, as you see, 0.018 Kelvin per watts. Using the same Q, because Q stays constant along that sleeve, we end up with that our T2 is equal to 75 degrees C. And again, this makes sense. It's getting hotter as you go towards the center. We could have also used the overall balance to find T2 and then found T1 as we did in the earlier screencast. However, as you'll see in the final screencast about radial conduction with generation, this approach won't work if you need a temperature within the rod.